Okay, diabetes. I guess many people know there's two types of diabetes. There's child onset type 1 diabetes and adult onset type 2 diabetes. Type 1 diabetes is insulin dependent. Type 2 diabetes is non-insulin dependent. So type 1, maybe we can just have a look at this figure here. Okay, we have normal situation in the pancreas. We talked about islets of Langerhans, beta cells produce insulin in response to raising glucose levels in the blood. Bind to the insulin receptor through pi3 kinase AKT signaling leads to translocation of glucose receptors to the cell surface in insulin responsive tissues and transport of glucose from the bloodstream rapidly into the cells, lowering again blood glucose levels. In the case of type 1 diabetes, the cells, the beta cells of the islets of Langerhans are destroyed early on in the child's life. This, I think, is likely autoimmune mediated and probably has some genetic predisposition, but is complicated then. They don't fully understand or it's a multifactorial combination of things that set this off. Predominantly occurs in childhood, characterized by severe insulinopenia, lack of insulin, and dependence on exogenous outside supply of insulin to prevent ketosis, lack of carbohydrates, and to preserve life. So this can be fatal. And in the old days, and if you look in the book, you'll see pictures, some black and white picture of the first child they managed to save via injection of insulin. There's a lot of interesting stories in the book on the discovery of insulin. Check it out. It's worth looking at. We're going to just go quickly through this part here. Now, type 2 diabetes, on the other hand, they still produce insulin, but they have insulin resistant tissues. So the receptor is not responding to insulin binding for a variety of reasons that we will have a look at, and therefore glucose is not imported into the cell, leaving blood glucose at a higher basal level, generally, especially after feeding. And as I said, others have said as well, glucose is a highly reactive molecule. That's why we like to get it out of the blood quickly and get it stored as glycogen where necessary to store it. Otherwise, it will start damaging proteins, reacting with proteins and damaging tissues. So patients are not insulin dependent, so it doesn't help to give them injections of insulin. So yeah, the type 1 diabetes, the typical treatment is monitoring your blood glucose and taking injections of insulin when blood glucose is high. There are other drugs that can be given instead of insulin. That was the classical one. We'll mention at least one other way of treating that. Yeah, so because they are not insulin dependent, they don't develop this ketosis, a lack of carbohydrates. Generally occurs after the age of 40, and there is a high correlation with obesity. So a high incidence of associated obesity, high correlation with obesity. Insulin secretion generally adequate. Insulin resistance is present. So the tissues stop responding to the normal amount of insulin. Even we'll see the body compensates. The beta cells start proliferating to try and produce more beta cells and produce more insulin. And still, at a certain time, it doesn't help. You go from being insulin resistant to diabetic. There is no associated genetic predisposition according to these notes, and I put in a question mark here because I think there is. And we'll just briefly glance at that. And genetic and epigenetic, we're not going to go into. Right? What causes it? A combination of genetic and lifestyle factors. So even here, some genetic and lifestyle factors. Scientists do not know the exact cause, but risk factors appear to include excess body fat, high blood pressure or cholesterol, having a close family member with the condition, suggesting genetic predisposition, a history of gestational diabetes. So this is a temporary diabetes experienced by some women during pregnancy. Higher age, so typically over 40 in the Western world. So testing for diabetes, if you had diabetes type 1, you're probably not going to need testing for it. You will be very sick as a child and it'll be diagnosed very rapidly these days. But type 2 diabetes, you may end up having to go to the doctor because you're feeling very tired, lethargic, um, and experiencing other problems. Then the doctor will give you an oral glucose tolerance test. And if we look at this, so basically they'll give you a shot of glucose. So you have to starve yourself, go overnight, starve yourself, don't eat anything for breakfast, go to the doctor, take a shot of glucose, and then he'll take your blood at different times to see how much glucose is in your blood. And what we see that the normal blood glucose is around between 60 and 90 milligrams per deciliter, and it quickly rises upon ingestion of glucose and returns to normal levels, even a little bit below, and comes up again. This is how the normal person would look. If we have the person with type 2 diabetes and we don't know how they look, first of all, their basal glucose levels can already be much higher, already in dangerous range. And then they take this shot of glucose and it spikes really high and takes longer to come down. So this is the oral glucose tolerance test that is worth knowing what's going on. Recognize type 2 diabetic people compared to normal. So diabetes, if left untreated, it can be very serious, lead to blindness, and it's very common that not so common here in Western worlds, but it can even in elderly people, because diabetes can go unchecked and undiagnosed, right? But for people around the age of 40, very uncommon that you see amputation. Typically, the feet and the extremities are very sensitive. They get damaged by the high blood glucose over time, and in the end, they just have to. It's just dead, decrepit tissue that has to be cut off, so they amputate the feet and stuff like that. So it's serious, and of course it can even lead to coma and death So there is a strong correlation between obesity and diabetes. And if we look at these maps from the Center of Disease Controls in America, America is very good for these statistics. So the obesity as classified by having a body mass index of over 30 kilograms per meter squared, BMI. You can see in the 90s, this is the color. The more red, the more obese people are. So at this stage, by 2010, 26% of adults aged 18 or over were obese, 26 or more in these states, right? So you can see over time, there's a development. Orange, they were over 22% in these states, and then 10 years later, they're over 26%. And 2010, 37.5% of US adults were obese. And then if you look at diabetes, and what I want, it's the same patterning here, we're coloring, and I want you to notice that the patterning sort of it follows. There's a bit of a delay. So in 1994, there's not as much diabetes, as high level of diabetes as there was with obesity. But by 2000, is quite similar. It's even gone past it. Here again, it's if you look at obesity compared to diabetes, it's following the same kind of pattern, especially here. 2010, compare obesity with diabetes, and you see that there's a pattern, right? So, according to the data from the WHO in 2008, 35% of adults aged 20 were overweight and 11% were obese worldwide. So, obesity is a problem when it comes, it's causative, seems like, of diabetes, and diabetes in the Western world is an expensive problem. It's expensive to treat. Here's just some rates as they go up over time. This is obesity rates. Put Norway in here, not doing too bad. 12% of adults were obese according to the BMI in 2016. So then I guess the amount of type 2 diabetes would be, much less than this, right? Maybe 5% or something. I don't have that data. Share of adults defined as obese 2016 worldwide. So, we're not doing too bad up here. A bit worse, but not as bad as the States or some other countries. You can go in here yourself, forskning.no, måtte hälsoövervikt lämnar som rammas av epidemi. So here, just briefly mention this, sort of about the genetic populations or the genetic factors if we look at different populations. So actually, Europeans in the Western world, diabetes in 2000 is actually pretty low. So if you look at Britain and Germany, it was about 2%. I checked now recently, and in Britain it has gone up to 7% diabetic, which is quite high, adult population. And then Australia, it was hard to get these good numbers. In the United States, gone from 8% to 13% of adults being diabetic. What was this? Yeah, diabetic. Yeah, not just obese, but full-blown diabetes. And what's interesting is sort of, well, first of all, Western rates are actually, I can't say they're very low, but they are lower than other ethnic populations, right? And what's interesting is some examples where you had these Pacific Islanders that lived off, it was a poor country, this Nauru, and was controlled by, it was a colonized country by the islanders, had no say. Finally, they became independent in 58, and then they went from being poor to being very rich, and spent all their money on Western food. They increased body mass index dramatically, and by 2002, 41% of the population was diabetic. You can see also New Guinea, just like they live in the jungle or they live in the city, the rate of diabetes shoots from 0 to 37%. And again, diet-induced diabetes or obesity. Then you have Aborigines living in Australia. If they live out in the outback, 0% diabetes. If they live in the city, 23% of the population gets diabetes. So environment is very important. This is something I mentioned at the beginning of the orientation meeting. We try and get an idea, does environment affect our metabolism? And yeah, it does. And genetics as well, right? Okay, back on target. So insulin resistance and how it can develop in different ways. This is one thing I mentioned already. So here we have a normal weight, 70-kilogram man with his pancreatic islets, and he puts on weight. He's still metabolically healthy, and his insulin levels have risen actually to compensate for this increase in insulin-sensitive tissue that needs the insulin to bring in the glucose out of the bloodstream. So we get a beta cell growth compensation. They expand the population of cells producing insulin, and over time they cannot keep this up, and it causes a lot of stress on the beta cells, and in the end they can fail. So you go from being metabolically healthy, and maybe you have insulin resistance developing along this stage, or first you're trying to compensate so you don't have insulin resistant tissues, then you can no longer, and after a collapse of the beta cells producing insulin, you go from obese to even full-blown type 2 diabetes. So what's interesting is that up to this stage, even insulin resistance and being overweight, it's a reversible condition, right? So weight loss and exercise can restore insulin sensitivity, and you can revert back to the normal situation. However, if you go into the morbidly obese situation and you lose healthy beta cells, they start dying off, then it becomes irreversible. Then you'll need medications like insulin is one and metformin is another one. There are other ways that have been speculated to also give rise to the development of diabetes. This is from the book. Here we see the condition of a lean 70 kilogram man or woman. In biochemistry, so it's the 70 kilogram man. Lean, triacylglycerol diet. You have small adipocytes, and they are supplying um, fatty acids to the muscle, and the muscle is also taking in glucose, both to get ATP out of it. Then, as you become overweight, actually your adipocytes grow larger, maybe an expansion of the cell population, so you have more of those cells and they grow larger. And still, you're insulin sensitive. Your muscles are doing work. Fatty acids come from the adipocytes. Glucose can go in, and then at a certain stage of being overweight, these adipocytes experience inflammation. They start. So some of the, to be more specific, some tissue, adipose tissue, is hormonally active, and we kind of alluded to this a little bit, that it was had endocrine functions, right? And we were only interested in the endocrine functions that were signaling to the brain or other tissues, but actually they are also an immune tissue, and they produce, for example, TNF alpha, and then this will attract immune cells to the tissue, acting like it was an inflammation, and they will start attacking the tissue and infiltrate, macrophages infiltrate adipose tissue in response to MCP1. Macrophages and adipose tissue produce, so they produce the TNF alpha, it says in the book, but actually this visceral, I don't know if I can show you the visceral area here. Where's my, there? This is the bad fat in this area, the fat that surrounds your intestines and body organs. You don't want expansion of that. That's the dangerous one when it comes to inflammation, because that's an immune adipose pool of cells, whereas fat in other places doesn't have this immune function. Okay, that's why they talk about taking certain measurements. This body mass index maybe isn't the best way. It depends where that fat is, whether you're healthy obese or non-healthy, or healthy overweight or non-healthy overweight. Adipocytes export fatty acids. Okay, in reaction to this, there's increased export of fatty acids that are taken up in the muscle, and they start interfering. The cells, the muscle cells are clogged with fat, and this interferes with GLUT4 transport to the cell surface, and this is one way in which you get insulin resistant tissues. Or this is another way, right? And then this, I think, is the last way. Insulin resistance due to overfeeding with a high protein diet. So here it's the complicated figure, but it's the one we're used to. Normally you have insulin binding to the receptor, activating pi3 kinase, activating AKT, leading to GLUT4 translocation of vesicles containing GLUT4 to the cell surface and import of glucose. And we mentioned this TOR pathway, that this, when insulin was signaling, normally was activating TOR, and S6 kinase had a feedback loop that decoupled the signaling on the intracellular side of the cell from the insulin on the outside of the cell, actually targeting IRS1, this adapter molecule that linked up to pi3 kinase, targeting IRS1 for degradation. Therefore, when you have high amino acids constantly fed state, they were also a way to keep TOR complex 1 active. Remember, TOR complex 1 was sitting on the lysosomes, sensing amino acids in the lysosome and the cytosol. When there's constantly a high amount of amino acids, TOR complex 1 is constantly kept on, and then shuts down insulin signaling in those cells, and then blood glucose is not coming in. So this is another way in which you can get insulin resistance in cells. And then I just indicate here, what about rapamycin? Could you use that as a therapy? Well, you don't really need to do that. I'll explain why after. So insulin resistance, yeah, this is sort of backing up what I've said here. I mentioned in a previous talk that the OB mouse, leptin mutant, they get big. They're used as a model for insulin resistance. And if we look at these players I just talked about now on Western blots, here we have a lean, here we have the OB mutant, and we look at S6 kinase, and actually TOR is a kinase, I mentioned that. It phosphorylates S6 kinase, giving us phospho S6 kinase. And we see that in the lean mouse, the phospho S6 kinase to S6 kinase ratios are about the same, whereas in the OB mouse, you have increased phosphorylation of S6 kinase compared to the total amount of S6 kinase. This is quantified here in measurement of the blots, and you see dramatic increase in the level of active S6 kinase in response to being this overweight. And what S6 kinase did, it was phosphorylating IRS1, targeting it for degradation. We see in the lean mouse 3 examples of IRS1 levels in cells, and in the OB mutant mouse, the levels of IRS1 in the cells is decreased because it's targeted for degradation, leading to insulin resistance in these cells. Insulin resistance due to activation of mTOR shortens lifespan, whereas insulin resistance due to inhibition of mTOR increases lifespan. Yeah, so that was we're not going to go into the complication with treating the patients with TOR would be they develop a different kind of insulin resistance. Complicated slide. It has a reason. Please stick with me. We've talked about AMPK, and actually AMPK inhibits mTOR. So AMPK is here. This figure we've seen before, insulin receptor signaling down to TOR complex 1. And AMPK, when activated, for example, when ATP levels are low, when AMPK levels are high, activates AMPK, which will inhibit the TOR complex 1 complex. And what's important on this figure is that AMPK activation actually gives us an alternate route to trigger the translocation of GLUT4 containing vesicles to the cell surface. So what good is this? Well, it means that under starvation conditions in the cell, you can still put the GLUT4 receptor on the surface and trigger import of glucose. And this can be useful in diabetes treatment in insulin resistant tissues. How? Well, there's a drug, it's called metformin, 50 years on the market, that is an indirect activator of AMPK. So you treat diabetic patients with metformin instead of insulin. It activates AMPK, blocks TOR, and triggers the import of glucose into the cells. This is indicated here. Interesting sidebar. Diabetics treated with metformin have from 25% to 40% less cancers than those that receive insulin as a treatment. Source here, and I'll come back to that. So, treatments for diabetes mellitus, weight loss is one, exercise is another via AMPK, metformin, the drug, AMPK activated. And then there was a couple of drugs we talked about that actually affect the potassium channels in the pancreatic beta cells. We just mentioned them and I put icapens on the URL. So there's a correlation between obesity, diabetes, and heart disease. So obesity, heart disease rates, not surprising. Obesity, diabetes rates, I hope now not surprising, right? Or probably not before. These things are widely covered in the news these days. What about cancer? So again, if we go back to these maps and we start looking for correlations between diseases and, just between diseases, and we take obesity as a disease and see how obesity compares to cancer, all cancer types, regardless of sex, male and female, all races. We see looks like there's a correlation there between obesity and cancers. In fact, Cancer Research UK tells us that when they list the preventable causes of cancer and the number of cases per year, smoking is, of course, the most preventable cause of cancer. You shouldn't smoke. Obesity is the second most preventable cause of cancer, causing in the UK over 20,000 cancer cases per year. This is just to sort of try to summarize years and years of research into one slide. Excess body fat seems to account for between 1/4 and 1/2 of the occurrence of many frequent cancer types, including colorectal, breast, endometrial, renal cell, and adenocarcinoma. And actually, if you look for enrichment of cancer types, mostly geointestinal tract cancers, right? So esophagus, everything, the GI tract, esophagus down to the intestines that are more affected, but it does affect other tissues as well. So obesity, especially with this visceral fat deposition, that's the one I talked about, MOG-Min, is associated with low-grade inflammation, which plays a role in the pathogenesis of diabetes and cancer. So low-grade inflammation is thought to be one of the drivers of cancer. So this is quite an indirect way in which being obese can lead to other types of cancer than the gastrointestinal tract cancers. And then I mentioned this, diabetics treated with metformin have between 25 to 40% less cancer than those who receive insulin as a treatment. So does that imply that insulin treatment can trigger cancer? So if we look at a PET scan in the brain where we feed them, again, radio-labeled deoxyglucose, we see that it accumulates in the area where we have this tumor. And what they say is that many tumor cells typically have 2 to 3 times as many insulin growth factor receptors as healthy cells, making them much more responsive to insulin and hence glucose uptake. So many cancer cells, they've had a metabolic rewiring. One of the reasons why we study metabolism and these metabolic pathways at all is to understand the differences between normal healthy cells and cancer cells. And one of the sort of striking findings that's an active area of research is the metabolic rewiring in these cancer cells. And I've mentioned some of it that's been known for many years, like this Warburg effect, that cancer cells seem to prefer anaerobic glycolysis instead of as a source of energy instead of aerobic glycolysis and the citric acid cycle, right? We talked about that earlier on. So cancer cells, they like a lot of sugar, therefore they've adapted and they express a lot of insulin receptor. Treating diabetic patients with insulin receptor, and insulin will drive TOR complex 1 and drive cell proliferation, mimicking cancer situation. So it can contribute to that. That's bad news. So what about patients with insulin resistance or on the way to be diabetic? Then you have the situation where if you have a cancer, you have a lot of tissue that is not taking up blood glucose and leaving that blood glucose for the cancer. So it will be very happy. So just having insulin resistance by being obese can contribute to cancer growth, right? Because just because you get one cell becoming carcinogenic and starting to grow doesn't mean it will survive. It doesn't have the easiest time there. But if you can change the environment for the better for the cancer cell, it will do better. So if you provide it with more glucose, it will do better, right? Food for thought. And then coming towards the end now, unlike any other major signaling pathway in the cell, every member of the insulin receptor, TOR, target of rapamycin, complex 1, signaling axis is frequently altered in cancer. And I just took a couple of examples here from breast, endometrial, and colon cancers. The rate of mutation of pt2, you remember, converted pt3 back to pt2, so it was a lipid phosphatase. And pt3 was downstream of PI3 kinase. PI3 kinase phosphorylates pt2 to pt3. This binds AKT and we get activation of downstream processes. P10 opposes this. So P10 mutation means you will have more active PI3 kinase signaling. And in breast, pt10 is found in mutated in 33% of breast cancers, over 50% of endometrial cancers, and over 50% of colon cancers. PI3 kinase constitutively active mutations, so then this pathway will be on even if you have P10, are found in 27% of breast cancers, 28% of endometrial cancers, and 13% of colon cancers. How many times they occur together? Not so much, right? So taking them together, then you can say in endometrial cancer, 54 plus 28, 74, 80, 74, 82. 82% of endometrial cancers have overactive insulin TOR signaling. Then we mentioned RAS being downstream of insulin signaling as well, right? This RAS, RAF, MAP kinase pathway, it's also mutated in 18% of breast cancer, 11% of endometrial cancer, 35% of colon cancer. We were up to 82 plus 11, 93% of cancers frequently have this mutation. Right? That's a lot. So there is a correlation between obesity, diabetes, heart disease, and cancer. I hope that if you didn't know already, that you can think along those lines now. At least I'm not saying I want to convince you of things, but yeah. So that I think brings us to the end of this part. Please stick around. I think I have some slides. Where we covered many different things in this. So what's important for the test? So it's good to take up when it comes just to these 3 lectures. This hypothalamic feedback regulation of feeding. Well, know the players involved and know what they do. So insulin, glucagon, leptin, ghrelin, know them at least. The stuff in the brain, the neural wiring stuff, I think is very interesting, but it's quite difficult, and I don't think there'll be anything on that on the test. I can't promise, but so these guys, adiponectin, a neuropeptide Y, it's kind of in this loop in the brain. I'm not so sure about that. Activate AMPK. Okay, how much time have we spent on AMPK? We'll have to put something in there. Gut bacteria? No, not really. Diabetes, obesity. Oh, sorry, diseases. Yeah, maybe some. Yeah, right. Maybe some. The aging stuff is too shaky to include anything. Cancer links. Yeah, you could always argue that it's not really metabolism, Fergal, but everything is metabolism, especially cancer. But anyway, yeah, at least diabetes is more covered in the book, I think. I don't know if the book spends that much time on cancer. You'll probably hear about more the cancer things in MOL200 or something like that. So, yeah. Content. So well, first of all, I hope that at the end of the course now you appreciated that we have spanned from the chemical aspects of metabolism up to the pathways and their regulation. We spent a lot of time on them. And then we spent a little time at the end discussing the environment, our behavior in the environment, and how it affects metabolism, right? Try to give you a big picture of how relevant metabolism is. I hope that we have succeeded somewhat, and I hope, we avoid this situation, the real Krebs cycle, where you learn the Krebs cycle, forget the Krebs cycle, and you learn the enzymes and glycolysis and forget the enzymes and glycolysis. Will you need to know all the enzymes in glycolysis? No. Will you need to know the key ones? Yes, you should, right? And then with the other part, I'm most interested in the connections between these pathways and their regulation. So, but I can really only speak for me. I will try to encourage people to stay away from memory game style questions and go more for comprehension style questions, understanding, right? That's what I think is important. Understanding, I believe you will take with you going forward. Memory, you will forget, and then the whole course really is useless. So we've done some remodeling to the course. I pointed out sometimes where we've done this. I understand it's very difficult for you to appreciate that because you didn't see what the course was like before, right? So yeah, I've tried we've cut the content and tried to keep what's interesting without rambling. And of course, sometimes it can be that it's more interesting for me than you. I'm sorry about that. But I think it's good that you get to, we're building knowledge here in the course, and it's good to not just build knowledge and learn things, but actually try and put that to use by understanding more complex things and see the use of it, right? I hope that sometimes you can get that, but we have to help you acquire this knowledge, and you need a broad knowledge base in science before you know what you're going to do going forward, and at times you need to be able to develop the ability to have a deeper understanding, develop a deeper understanding, right? You need to have a broad knowledge, and sometimes you need to go deep in certain aspects. You need to learn how to do that, or see if you can do it. Maybe this is not your stuff. Later, you can decide your interests more and focus on them, right? So you can decide a master's that you want to do in a lab you think is interesting, or you can decide a PhD, maybe. It's hard to get a PhD that you think is very interesting, but you could be lucky, or you go and work in a lab, or. So that's this. We're mostly making the course for those kind of situations. We're not making the course for you going out of science doing other things, right? We have the generic skills aspect with the semester assignment, and that's to help people that take different choices in life as they go further. Speaking of that, it does feel at times like the semester assignment is a bit of the odd one out when it comes to focus on the course. We have the book and we have the colloquia and lectures, and really, the colloquia and the lecture and the book together are focusing on the exam, whereas the semester assignment is a bit hanging on the side. But it has these generic skills there, and we try to put content in that can be relevant for the course and easily enough digestible for you to see that relevance. And it's not the easiest thing. I don't know how well we succeed with that. So the exam will be based on the lectures, which are based on the book. We will have questions from or similar to those in the colloquia, but there can also be multiple choice and fill in the blanks. But in those cases, they will be based on the sort of, if you've met longer questions in colloquia, we might remodel it so that it's multiple choice. So hopefully you've learned and understood that and are able to address it in a different format. The exam I'm planning will go section-wise as we have covered the course. That might help you remember things a bit more. So we'll start with energetics, like I did for a couple of lectures. It'll be the first section of the exam. And then glycolysis will be the next, and then a regulation of glycolysis in sections in the exam. And then you'll know, if you haven't covered that, you can have a look at it, but you're probably not going to be able to answer much, So if you haven't covered all the lectures, those sections will be identifiable. You won't have to waste time looking at questions there, right? Then you have to consider each section will carry, 15 to 20 points, maybe more. Those, if you haven't covered that section, those points are gone. Consider that when you're thinking about your grade afterwards. In general, I'll say some of these things at the Q&A coming up. Try and address all the questions first, and then if you have time at the end, use time to improve the answers. Read the questions carefully, but we will not have trick or cryptic questions trying to fool you, even if it's multiple choice. You just try and read carefully, take your time, allow time for multiple choice. See the sections, say there's 5 sections that match the colloquia. If the exam is 3 hours long, each section give the same amount of time. Unless you don't know anything in one section because you didn't go to lectures or colloquia, forget about that. That's gone, right? And focus on the other 4 or the other 3 and try and get your 50-60% if that's where your goal is. Yeah, okay. So if you don't understand, even though I promise they're not going to be trick or cryptic, if you don't understand, ask try and ask a question of the examiner there, and they can send a message to me. However that works, I'll be available during the exam anyway. But and then you have to ask a specific question, not what's the answer. You have to ask, do you mean X or Y in interpretation? Or the alternative is, if there's no option to get a message through to me that there's some problem, indicate in your answer how you have interpreted the question, and we will take this into account. Okay. Thanks, guys. I hope you've managed to keep up and share our vision for the course and what biochemistry means. I'll see you in the, hopefully, please come to the Q&A section. Submit your questions in advance if you have specific questions. We will have a limited amount of time, so we will not go through sections again, but we leave all the videos up that we've made. So that's the benefits of these flipped teaching approaches. You will have the resources available when you need them, even if you haven't managed to keep up. Maybe they help you, okay? Hasta la vista.